All right, guys, can you hear the audio? There's only 4 people here, but we can start. I just want to know if you can hear the audio here. All right, Yusria, thanks. Okay, since you responded, Yusria, do you want to? I just made up some questions on domain and range. Did you have specific questions you want me to go through? I can go through those, or we can try some of the domain and range questions here. It's up to you. Sure. Okay, I'll run through these together. And anyone else, please let me know if you have questions. Okay, so I start off here taking a look at the idea of domain, and that's the focus of these questions. So whenever you're looking for domain, if you guys remember, when you're looking for domain, you want all the values such that the function exists. So if I look at A here, I'm interested in all the values such that this function exists. So the question becomes is where does it not exist? Well, it does not exist in values where you're dividing by 0, taking the root of the negative number, or the function itself is undefined. So in this case here, if you look at this, there are no values that I'm taking the root of a negative number, and there are also no values such that I'm dividing by 0. So for something like this, the domain for A is going to be all real numbers. Okay, so that's the answer for A here. We have all real numbers. If we move on to something like B, for B here, the same idea. The domain of this, you are in a situation. I need a bit more room here. For B here, we're in a situation where we can't take the root of a negative number, so therefore x plus 2 must be greater than or equal to 0. But also, we can't divide by 0, so therefore x plus 2 has to be strictly greater than 0, or x is strictly greater than negative 2. So for this one, the domain is going to go from negative 2 to infinity. For this one here, this would be your answer. So that's the answer for C. If you're taking a look at, or for B, I should say, it's the domain is greater than negative 2. If you're looking at D here, remember your logarithm, regardless of the base, your logarithm, if the base, in this case here, this implied base is 10. So in that situation, your logarithm looks something like this. So you have to be in a situation where you'll notice that the domain of your logarithm is greater than 0. So it has to be the case that 100 minus x squared must be greater than 0. But what does 100 minus x squared look like? Right? 100 minus x squared is a quadratic that opens down, looks something like this. So what I want to make sure that that is greater than 0. So I'm interested in all of these values here that I've highlighted in red. So that's going to be exactly between -10 and 10 you're going to get here. Yusria, so far are you with me with these three here? So the domain for this one, good. Okay, so here's A, B, and C. And like I said, the idea with the logarithm, it has to be the case that 100 minus x squared is greater than 0. So I quickly sketched the parabola and I saw that it's above the x-axis between -10 and 10. That's got to be the domain. So that's the domain for C. Lastly, for E here, you'll notice if you're taking a look at D, I'm sorry. If you're taking a look at D, this is just another way of writing 1/2 to the power of x. So this is just an exponential decay function. It's going to look something like this. So you can see here there's no issues with the domain. The domain of this function is all real numbers for D. You'd have all real numbers for that one. Okay, so there's examples of domain. I threw in some examples of range. Let's do them here so there's some room. We can go back and do inverses. But I had made up some examples for range as well. Yusria, since you're the one responding, did you want to try these yourself? Or did you want me to go right to just going through the explanations of them? Sure. So this part E here, we're taking a look here. They want to the negative x. They're looking for range. So with something like this, I'm going to want to sketch this. I just talked about 2 to the negative x is the same thing as 1/2 to the x. So it's an exponential decay. It's going to look like that. So the range of this function, right, where does it go? It gets as low as 0 and goes to infinity. So the range is from 0 to infinity. And notice I have open brackets on the 0 because that has a horizontal asymptote at 0. Right? As x gets infinitely large, your function 2 to the negative x approaches 0. But it's a horizontal asymptote at 0. Sort of like a right-sided horizontal asymptote at 0. So the domain for this, like we talked about, goes from 0 to infinity. If we take a look at F here, they're asking, so this is log base 1/2. I want to remind you guys of this. You guys know that this represents log base 10 of x, right? Because it comes from an exponential growth function looking like this, like 10 to the x, right? That becomes your log base 10 of x. But that's not the case here. This is coming from an exponential decay function. All right. Okay, just making sure everyone's with me here. All right, sorry, I thought it was slowing down there. Here, let me. I wanted to see if I could copy and paste the graph for you, but it'd be too difficult. All right, so anyways, this is from an exponential decay, like we were saying. So this will look something. This is your decay. So in this case here, the log will look something like this, and this is log of 1/2 to the x. So the range of this function right here of your log function, actually both log functions, the range of these functions is all real numbers. Right, so for both of these, the range becomes all real numbers. That's base 10, and this is base 1/2. Okay, so we have some examples here of domain. I've given you, what is this, 4 examples of just various domains to calculate. You have some ranges here as well to do, so make sure you're like aware of that for the exam. Moving on to inverses, I thought we'd do some inverses because I realized a lot of you guys might not have practiced your inverses. The idea with inverses and to calculate an inverse is you have to interchange the x and y values, right? Because your inverse, as I just showed you over here, to calculate your inverse, it's the reflection in the line y equals x. That's how you get your base log base 10 and log base 1/2. Right here is the reflection in the line y equals, in this case, 1/2 x gives you your log base 1/2. And if I want log base 10, it's a reflection of 10 to the x. So when you find your inverse, you're flipping that in the line y equals x. So if I want the inverse of the left-hand side one, what we're going to have to do here is flip your x's and y values. And you have to be able to solve for y, so I have to get y by itself. So the technique here was to, we actually ended up completing the square for this one. So if you remember how to complete the square, you take your b value, which is 1, you divide by 2 and square it. So minus 1 over 4 plus 1. So going through and calculating my, completing the square here, I can go ahead and calculate my inverse, right? To find the inverse, you interchange your x and y values. That's what I did here. Then I went ahead and completed the square. And after I complete, now that I've completed the square, I can now isolate and solve for y. So I can subtract 3/4 on both sides. And then I can take the square root. And I can isolate for y. Wahab, hello. Sure thing, sure thing. So for completing the square here, let me go over that. So to complete the square, you have yourself a quadratic. Let's say I just kind of write any old quadratic down. What you do is you identify your b value, which is 5 in my example here. You divide it by 2 and then you square it, which in this case is 25 over 4. So that becomes the number that you add and subtract. So I'm going to go ahead and take this. I'm going to add 25 over 4, subtract 25 over 4, and add 1. So I've kind of added and subtract that, and as soon as you do that, the first three terms become a perfect square. I can rewrite this as an expression to the power of 2. This becomes x plus 5/2 squared. Excuse me, by doing that. And then this becomes minus 21 over 4. And now I've completed the square. All right, is this okay? The idea of completing the square? Good, 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 good. Okay, so that's sort of how I got this here, is I've got this, but this is not a function. Right? Remember, when you take your inverse, you don't always get a function. If you remember, when you take your inverse, sometimes you have to restrict the domain to make it a function. So like, for instance, let's see if I can get some space here. Like right here, for instance, if you look at like y equals x squared, okay, that looks like if I were to sketch that, it would look something like this. This is roughly what y equals x squared looks like, right? And you guys know that if it fails the, I don't know if you remember this, but, oops, sorry. If it fails the horizontal line test, then the inverse is not a function. You guys remember that? So like a lot of times we would have to restrict the domain to make it a function. Like we'd say like, let the domain of the function go from negative infinity to like 0. And then in which case my function would only have like one side to it, like that. So then it would pass, and then the inverse would be a function. Right. See, now it'll pass the horizontal line test, and the inverse is a function. Those are some things that we had talked about. So like like on the exam, be able to calculate the inverse of a function. If you get a graph, like visually you can see whether the inverse is a function. You know, be able to restrict the domain such that that happens as well. Okay. I didn't get to this one, and I definitely need more room for it, so put it right here. And in this situation, they want us to find the inverse of this one. Do you want me to let you guys try this one? I mean, it would be worth it to try to actually calculate the inverse of this. All right, I'll give you guys some time to try that. We can take it up. It would be good practice. All right, I got my answer here. I'm not sure if it's on your screen. There's always a little delay between when I write and it shows up, but I'm getting 5x over x minus 1 here. Okay, is this good? Those of you who are asking here, do we get this inverse? All right. Okay, are there specific questions? There's not like a lot of people showed up. We only have 5, so if there's not a lot of questions, we can log off and be done then. Yeah, for sure. Yeah. Okay. All right. You three with yours. The idea is um, log base 10 of x. If you're looking at log base 10 of x, the idea is it looks. This is what log base 10 of x looks like. Right. This is what log base 10 of x looks like. Um, and you three are gonna have to like text and respond if you want me to explain these. Right. So jump in when you don't understand. You just have to type it out, and then I can respond and quickly. So I'm asking for the range of this. The range is your y values. This is what log base 10 of x looks like. So the range here is all real numbers. So if I look at this question, the range of this function is all real numbers. You can see it here. Like this continues on to negative infinity, and this goes up to positive infinity. So that's log base 10 of x. The point I was making is if you're looking at log base 1/2 of x, I was saying it looks a little different, right? It's going to look like this, log base 1/2 of x, but it has the same range. The range is unchanged to this. The range of this is also all real numbers. Makes no difference. Have the same range for both of these. That's all I was getting at. Is like be able to be able to understand they look different, but they still have the same range. Same range, same domain. Um, Adam Hyatt Adam. I still don't even know who is Hyatt Adam. Not really sure. Still don't teach a Hyatt Adam. But look over the domain and range worksheet from number unit 1, 7, and 8. Let me see if I can load that up. Oh, hey, me here. Sure, if people need help, that's fine. Exam information. Okay. Okay, so number 7 and 8, you said? 7 and 8. Oh, okay. Yes. All right, so Hyatt, is it these two questions you're looking at? These 7 and 8 you're asking? Sorry, excuse me. Okay, so for 7 here, they give you have a function. They give you this function f at x. In this case, it's 5 minus 2x plus k. And they tell you that when you f composite f at k is 13, that's like given to you. And they want you to find the function at 4. So first of all, what is this, like f composite f at k is 13. Let's find, like, what is f at k? Well, f at k is going to be 5 minus 2. Everywhere I see an x, I change that to a k. So you get f at k is 5 minus k. Right? F at k equals 5 minus k. So therefore, from here, f composite f at k is going to be f at 5 minus k. And what is f at 5 minus k? What you do is everywhere you see an x in your function, you're going to change that to a 5 minus k. So it's going to be 5 times 2 times 5 minus k plus k. So you just kind of go through your math here. This becomes 10 plus 2k plus k. I end up getting here, what is this? 3k minus 5? I end up getting for, so I now know, probably wondering where this is going. I now know that f composite f at k is equal to 3k minus 5, but they told me that's equal to 13. So therefore we have 13 equals 3k minus 5. So k is 6. I know k is 6 here. Are you following this one? It's kind of like working your composition, just kind of working through your composition practice here. So I end up getting this is 11 minus 2x. And you end up getting 19. Does that make sense, the steps there? Or like jump in where you're having trouble? Really? Okay. Are you sure? I feel like, okay. If you got it. Number 8, don't worry about number 8. Like that's not something you have to worry about for the exam. Like number 8's a little much. Not really a little much. We covered it, but you don't have to worry too much about 8, at least on my exam. We kind of have other things to focus on. Composition of functions is obviously on, but not like, it's like a specialty question like that. And Wahab, you're asking if we could go over where we're given a set of coordinates and we have to find the domain and thank you, yes. Domain and range of the sum? Oh, sure. Sure. I'll have to make one up for you, Wahab. Are you still there, Wahab? I can make one up. All right, let's see. Example. Like for example, Wahab, if you look at this here, I've defined a function like f at 1 is 2, f at 2 is 4, f at 3 is 6, g at 1 is 8, g at 3 is 0. And they're asking you for, let's say we wanted f plus g on like 1. Oh, the domain and range. Oh, okay, yeah, we had kind of touched on that. To find the domain, you have to find out where both functions are happy. Function f is happy at 1, 2, and 3. Function g is happy at 1 and 3. So the domain is like where they're both happy, and they're both happy at 1 and 3. That would be the domain of f plus g. But like if I ask you for the domain of f minus g, it's the exact same criteria. Like they both have to exist. So the domain of f minus g is the same as the domain of f plus g, and that's the same as the domain of f times g as well. Makes no difference. People from Mr. Coulter's class are coming to this live. Math Turtle is goated. F times g is the same, but Wahab, the domain of f divided by g is different because 1 is good, but it's just 1. The reason why is like f over g, if it were to act on 3, it's going to be the function at 3, f at 3 over g at 3. F at 3 is fine, it's 6, right? F at 3 is 6, but g at 3 is 0, and that's undefined here. So the domain of f over g is simply just 1. So very good question. Oh, I know me here, yes. Is this good, Wahab? Kind of a good question. Grapes on a tree. Yes, grapes on a tree. Very nice. Okay. And don't go to Wahab, can you tell me who Hyatt is? Because I don't teach a Hyatt or an atom, and definitely not a Hyatt atom. I'm still trying to figure out who this person is. Hyatt. I don't know. Me either. All right. Anyways, Wahab, with these questions, don't go insane. Like spend a ton of time practicing. Just know the basics. If I give you something like this on the exam, like this, like it, simple, like what you see here. Like I know we had done a lot more. I think I did it. Maybe a little more complicated, but something simple like this, you're good if you get the basics of it. Is this okay? All right. What's next? Okay, good. Good. All right. Is there anything specific? Like, is there a specific topic people would like me to talk about? Like specific questions that they're kind of looking for? What else can I help you guys with? Or I think I've covered everything people have been asking. Okay, very first worksheet. Composition. Oh, sorry. Were the first two range examples the same answers? I gave you 3 range examples. Ustria. I took these 2 up with you. They're both all real numbers. The range of this one was from 0 to infinity. 197. This is from the Nelson book, right? Or that, do you mean algebra and trig? Sure thing, Yusri. First, I'll just take care of Wahab's question. 197. Okay, you're asking algebra and trig. All right, let's take a look here, Wahab. Oh, wow, we already did a lot. All right, let's take a peek. So page, yeah, got it. 197, you're looking at 33, 53, and 55. Okay, so 30, and Yusri, I'll get to yours in a second as well. So for 33 here, yeah, you guys have asked this before when we, in the unit, it was a popular question people had asked. So they give you f at x is, you have -6, g at x is 12, and we're finding composition here. So it's just a bit awkward maybe, like you just got to stick to the definition. So f composite g at x is going to be f acting on g at x, while g at x is equal to 12. But my function f at x, the function here f at x equals -6. It's gonna output a -6 no matter the input. So in this case here, f composite g at x is -6. If you look at it the other way, you do g composite f at x, it's g acting on f at x. Well, you know that f at x is -6. So now what happens is the function g is acting on -6. That's regardless of the input. No matter what you get, it outputs a 12. So this will output a 12 just the same. So for number 33, f composite g is -6 and g composite f is 12. And then you're looking at 53. Okay, so for 53, they give you 3x plus b. F at x is 3x plus b. G at x is 2x minus 1. And find b such that it's commutative, the composition. So they give these two functions. They want you to calculate f composite g at x, calculate g composite f at x, and show their equals. This is going to be f acting on g at x, which is f acting on 2x minus 1, which is 3 times 2x minus 1 plus b. Right, so when I calculate this, I get 6x minus 3 plus b. So I know that f composite g at x is 6x minus 3 plus b. And if I go ahead and calculate, excuse me, g composite f at x, it's going to be 2 times 3x plus b minus 1 is 6x plus 2b minus 1. So I did composition both ways. If you equate these two, if I set these two equal, you'll see the 6x's cancel. I get 2b minus 1 equals negative 3 plus b. Or in other words, b equals negative 2. So for these functions to be commutative with composition, for 53, b has to equal negative 2. Kind of interesting question. This okay? Well, how would you think of 53? I can't tell the delay, if there's a big delay on this or not. Let me see. Okay. All right. Okay. And then 55. Yeah, and that's how I got the negative 2. Very good. Yep. So for 55 here, we've got this 1 over 1 minus x function. And they want you to find, they have you do the composition a bunch of times. So they want f composite f at x. So this will be f acting on f at x, which is f acting on 1 over 1 minus x. Right, so you just, everywhere I see an x, I'm now changing this to a 1 over 1 minus x. Looks like this thing here. I didn't do elimination. I just, when you equate these, you can see the 6 x's cancel right away. So I was left with 2b minus 1 equals 3 minus b. So then I just brought the b over and this over, and I got b as negative 2. That gives me commutativity, like the f composite g and g composite f are the same. For 55 here, Wahab, I'm just doing composition. So everywhere I see an x, I change this 1 over 1 minus x. So you just have to get a common denominator. It's a bit messy. I'm gonna move this question down here. You can see you just get a common denominator. The ones will cancel. Multiply by the flip. And then push that 1 to the top. And now I know that f composite f at x is x minus 1 over x. And then I think in 2, it's f composite f at x they ask for 55. Well, that's going to be f acting on f at x. Well, we literally just did f composite f at x, we know, is x minus 1 over x. So recall this is the original function. So I just did this one right here. I know that f composite f at x is this x minus 1 over x. So now everywhere I see an x, I change it to 1 over 1 minus over x. Now I can go ahead and get a common denominator for this one. You just get x back. Right, so that's what happens in 55. The second composition is x minus 1 over x. The third composition is x. So the fourth composition will kind of bounce back and forth now between these two. It will be bouncing back and forth between these compositions now. Sure thing, we'll have Nelson 52. Number 14. Okay, so page 52, number 14 here. Oh, yes. Someone had asked this today. So with this one here, they're asking you to, show there's no way for this to be continuous. The idea here is this is a piecewise function, so it's created from 3 different functions, right? You've got 2 different types of linear functions, and then you have like a quadratic. But for these to line up, these breaking points here have to, like at -1 and at 3, they've got, the function's got to line up. Well, the function at -1 is equal to, it's going to be this one, right? The function at -1 is going to be -1 plus k. Right, there's my function at, there's my function at -1. But as I approach -1 from the left-hand side, this will approach, and I can sub that -1 into the 5x, giving me -5. So therefore, I know for these to line up, -1 plus k has to equal -5, or k equals -4. Or k equals -4. So therefore, for these two to line up, k has to equal -4. But if k equals -4, my function now looks like 5x, x minus 4, and this 2x squared, right? It has to be the case. X is less than -1, -1 is less than x is less than or equal to 3, x is greater than 3. So with k being -4, the question is does it line up here? And you'll find it doesn't, because if I evaluate this at 3, I get 3 minus 4 is -1, but as I approach 3 from the right-hand side, this becomes 2 times 3 squared, right? And -1 is not equal to 18, because that's equal to 18. So it doesn't, like if you need the -4 to get continuity at the breaking point here, that same value won't give you continuity at the 3. There's like still a break in the graph. So it's impossible to have continuity for this piecewise function. For this example here, you have a piecewise function. I want to make sure that these line up. The only spot that they could break, the breaking point is at -1. So I want to find a value of k that makes this work. So if I evaluate the function at negative 1, you get negative 1 plus k, right? Like if I let x be negative 1 here, you get negative 1 plus k. As I approach, as this approaches negative 1, this becomes negative 5. So by equating these two, you're finding the value of k that makes these two linear functions line up. So right at negative 1, when x is negative 1, these touch. To do that, x has to be negative 4. But that same negative 4 value doesn't do the trick here. Because when I let x be negative 4, that's what we have down here, we do not get equality. We do not get equality. When I let x be negative 4, if you check this at 3, subbing 3 into here and 3 into here, you do not get equality. A 3 into here gives me negative 1, a 3 into here gives me 18. Right? So the negative 1 into here gives me negative 5. A negative 1 into here gives me negative 5. That gives you the equality, so they're lined up. Doesn't happen for 3. So it's impossible to make this work. No matter what, the function is going to be discontinuous. That's the idea. And I had mentioned I can see number 15 says greatest integer function. That will not be on the exam. You do not have to worry about the greatest integer function. Okay. All right. I think we'll stop here. Like I said, not a ton of people showed up, so we'll do the next help session the night before the exam. I'm sure it'll be busy then, and I can help a bunch of people. But we'll stop here today. I'll save this stream and try to timestamp it for you guys so you can kind of bounce through the questions that we did work on. It's about an hour long, so I'll try to break it apart so you can check out specific topics. But we'll stop here and set up the next one. We can do it right before the exam. I'll do it for both periods. So the Tuesday and Thursday night, we can do one of those. I'm sure there'll be a bunch of questions, and we should be good. You as well, Mihir. I'll see you.